should be enough, but they're probably, I'll ask whether there's some spares lying around.
Thanks very much.
Okay. This is handout 1. Handout 1. Handout 2, there should be too many around. Some people have taken more than one copy. Okay, good morning everyone. Let's get started. First of all, today there definitely should have been sufficient handouts unless suddenly more people want to listen to CP1 than have enrolled. If you have taken more copies than you actually need, please pass them down. There are a few people without, yeah, there's one coming. There are a few people without handouts. There's another one. So yeah, please try to redistribute to those who don't have a handout. The handouts are usually put up here in front. So unless you want to climb the stairs twice, it's worth always to picking them up when you walk into the lecture hall. And if there are any spares, like this is lecture 1, in case you don't, whoever they can pick up here in those racks, you can usually find the leftover notes from the courses. So here are a few more spares in case you don't have. Anyone else? Oh, you. Okay. This is the one thing. The other thing is I got asked whether I can upload the lectures not in the morning before the lectures, but the day or the evening before. I'm trying to do that if you want to have a look at the webpage before. The next lecture will be next Monday morning, and I'll try to upload it on the weekend. So in case you want to have a look at the notes before you come, you can do this. Last but not least, that's a different slide. I'm not sure whether you've heard about it, the Physics Undergraduate Ambassador Scheme, where you can get engaged with outreach activities. It's on. And in outreach activities, setting up new experiments, playing around. Duncan, you don't get any signal? Apparently it died again. I'll fix it otherwise. Sorry for that. Now, oh, yeah. Now it's definitely on. And yes, Catherine Boast, who's running the scheme in the physics department, will be around at the end of the lecture between 9:55 and 10:05. So if you've got any questions about that and if you're interested, you can ask directly her. Now, let's go to the lecture then. So we'll be more on vectors today, but we'll also do some first examples. The outline, scalar product, dot product, differentiation, and then a couple of examples. So as Jester said yesterday, the vectors are defined by a magnitude and a direction, whereas the scalars are only defined by magnitude. The scalar dot product is extremely important in many applications of physics. You will see that and make use of that later. So the definition of the dot product is A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. So as drawn there, if that's vector B and vector A, you've got the angle theta in there, and if you want to write it shorthand, A dot B dot cos theta, just writing the magnitude there. The result is a scalar, or scalar dot product. You don't end up with a vector there. Well, it's quite obvious what you get if A is perpendicular to B. You get 0, because then the cosine of theta is 0. Similarly, the magnitude of the vector is given like this, or the square of the magnitude of the vector, because theta equals 0 degree. So if you want to get the magnitude of a vector, you take the square root of the dot product. And it is, as the graph shows on the bottom right, you have the projection down on the vector A times the magnitude. And you can, of course, since it's symmetric, also do it this way, as long as the 90 degrees. And then you can work out with the scalar dot or the dot product. Now, the properties of this scalar product are pretty straightforward. Well, I probably don't have to write it down. It's all written in here. So as before, if we take the unit vectors I, j, or k, if you dot them with each other, then since they are parallel and they have the magnitude of 1, we basically get directly 1. And if they are perpendicular to each other, again, the unit vectors in the x, y, and z direction are perpendicular, you end up with 0. If you want then to write it out as components, a dot b, yes, you can write each of those vectors out in ax, I, aj, y, j, and so on. And then you end up, this is basically the dot product. If you want to abbreviate it, often it's written in the summation notation, I equals 1 to n, where n is the dimensions, ai, bi, and that's also sometimes written as a transpose b. And what do I mean with transpose? If you've got the vector a and you write it as ax, ay, az, and you do the transpose, it's just ax, ay, az. They have to have the same dimensions. As you can imagine, adding a vector from 2 dimensions to a vector in 3 dimensions doesn't work out. Similar, like you should not add kilograms and seconds in any equations. And if you stumble across one of those in your problem sheets, then you probably have gone wrong somewhere. Now, the dot product is commutative and distributive. You can easily work that out if you just plug it in here, the numbers, then it's going to. But parentheses are very, very important. The dot product gives a scalar. So this is basically a scalar times the vector w in this direction, whereas this is a vector in the u direction. And you have to be a little bit careful there with the brackets. Often you come across that you want to have what is the length of the addition of 2 vectors, and that's basically a squared plus b squared plus 2a dot b equals a squared plus b squared plus 2ab, and then we get again the cos theta in here. So those are the basic properties of the scalar product. The other you want the handout? No. Feel free, there are spaces around. This is one of the key products of vectors. The other one is the vector product or cross product. So here is the definition, again written. This time it's the magnitude of A times magnitude B times the sine of the theta between them, but very important, there's this n, and n is a vector perpendicular to both A and B. So whereas the dot product works in any dimensions, whether it's 2, 3, or 10 dimensions, the vector product is only defined in 3 dimensions. Physically very, very relevant. Angular momentum, torque, I have an example later. Lorentz force, charged particles, you will come across it in many. So what's written down there in terms of getting the direction of the result, so getting the direction of this vector n, this is the way of doing it, and it's a safe way of doing it. It looks a little bit silly when you're sitting in the exam and then you start, well, vector 2 and trying to get the direction out, but it's the most reliable way, at least for me, to figure out in which direction it goes. So if you have this vector A and B and an angle theta between them, thumb in direction of the first one, index finger in the second one, and the middle finger is then going out of the plane or out of the direction, and that gives at least the rough direction in which the A cross B is going. The reason why we use the right hand there is we usually have right-handed coordinate systems where we've got x, y, z spanning up x, y, and then z on top of it. And it is really, really relevant in many, many physical problems. So similar to the dot product, we quickly go over the properties of the vector product. I cross j equals k, j cross k equals I, k cross I equals j. And if they are, if you are parallel, then you get a 0. If you swap the order, well, we'll get to that. So if you swap the order here, I cross j equals k, if you change that j cross I, you get minus k. Again, you basically start setting it up the other way. Instead of you swap the two vectors and then you get the negative. So this is shown here, the non-commutative part. Distributive, if you've got those vectors, then it works quite straightforward. This is extremely important. Again, the brackets are important here. Non-associative, so you can't simply swap the brackets around because the vectors will be in different directions. An m is a scalar. Again, it works out. Good morning. M is a scalar. You can basically move it around. That's pretty straightforward. And if A cross B equals 0, then they are 0 or 180 degrees. And that's also why the reason why those unit vectors, if I use both in the same direction, if they're parallel or anti-parallel, then it's 0. A cross B is maximum. So max for A perpendicular to B, whereas the dot product that leads to 0, this now leads to the maximum, and the length of A cross B equals simply A times B or AB, if we just drop that. Now, if we write those vector products and components, often we are only interested in a component in a particular direction. It gets a little bit tricky because you want to figure out which components actually count to the y or z component of the result. Now, if we write A cross B equals, I'm just going to write that out, AX, AY, AZ cross BX, BY, BZ equals, going to introduce now the unit vectors just to make it clear, AX in the I direction plus AY in the J direction, or in the direction of the unit vector J, and AZ K cross, and the same for the vector B, BXI plus BYJ plus BZK. So if we now work that out and use I cross I equals 0 and so on, and I cross J equals K, and we use those relationships, we basically end up with A cross B equals AYBZ minus AZBY in the I direction plus, minus AXBZ minus AZBX in the J direction plus AXBY minus AYBX in the third direction. So how do you get the order right? I've always been struggling with this, but there are two ways in ensuring that you don't mix up those terms here that go into each of the components. So the easiest bit is to find out which subscripts go in there. So we are here in the x direction. You notice the x doesn't appear here. We are here in the y direction. No y is appearing here. And we are in the or in the z direction, and no z is appearing here. That has to do with this relationship that if you take I cross I, it's 0. So that's easy. But how do we get the signs right? And that's as usual in physics. Physics is usually a factor 2 or a minus sign off. So there are two ways. The one is written there is the determinant form. Not sure whether everyone has seen a determinant. So determinant, or short det of a vector, a matrix A. This can be done for every square matrix. Can be done for every square matrix. If we take a 2 by 2 matrix, so A, B, C, D, it is basically this diagonal. Let me pick a different color. So this is one direction, the other one is the other direction, and the one that goes from top left to bottom right is the plus. So this is AD minus BC. And if we do that in the 3 by 3, A, B, C, D, E, F, G, H, I. You basically do the same. You look at those directions and flip over if you don't have 3 in one row. So A, E, I plus B, F, G plus C, D, H. And then the opposite direction, you have the minus signs. And yeah, those are the 3. And then you have minus C, E, G, that's this one, minus F, H, A, that's F, H, A, and B, D, I. And you can also use that for writing out something unclear. If you have any questions, feel free to interrupt me. If I now write that and use that for the vector product, I'm basically rewriting the whole thing as I've got I, J, K, and then A, X, A, Y, A, Z, B, X, B, Y, B, Z. And if I now do this and work it out, I get the right order of the determinant. So if I look at anything that's going into the I direction, I have A, Y, B, Z minus what else is in the I direction, A, Z, B, Y. So minus A, Z, B, Y. And I'll continue that through and I get the right order of what has to be plus or minus sign. So this is one way. A little bit more advanced way, which you might come across at some point, and some of you may have already come across, is the Levi-Civita symbol, epsilon ijk, which is defined as +1 if these indices I, j, k are so if they are 1, 2, 3, 2, 3, 1, or 3, 1, 2. So basically, if I always count up, 1, 2, 3, 1, 2, 3, 1, 2, 3. Just the permutation, but always counting upwards. It's -1 for the opposite. If I basically have 3, 2, 1, and its permutations 2, 1, 3, and 1, 3, 2. And it is 0 else. So that can become quite handy and quite useful at some point. And I can write the ith component of this A cross B. The ith component I can write as sum j equals 1, 2, 3, since we're in 3 dimensions and it only works in 3 dimensions, k equals 1, 2, 3, epsilon I, j, k, a, j, b, k. So I'm looking at the ith component here. I have it here at first one, and then a jk component j and component k of the vector a and b. And if I follow Einstein's notation, I basically just drop the summation sign, because from the context it is clear. So the ith component of this vector is epsilon I, j, k, a, j, b, k. And then if I look at it at A cross B, if I look at the first component, I get that this has to be A2, B3, or Y and Z, minus A3, B2. And I can work my way through this with all the components. It looks a little bit tedious right now, but it becomes very useful if you have to do quite some summations over different vectors and have to figure out what, for example, A dot B cross C is. And if you can basically simply write that as epsilon I j k A I B j C k. And then you know what you need to sum up over all the permutations and which components get together there. So these are the two ways of getting then the real result of the vector product. The three-finger rule gives you the rough direction and lets you check the underlying physics. Often the rough direction is sufficient to find out whether you're right or wrong. But then to work out the actual magnitude, you need this. Now, examples of scalar and vector products in classical mechanics. So scalar product is, for example, here the definition of work done. We have a force F. We move a body a distance dr, so a small distance from position 1 to position 2, and the work done is this one. What it means is if I do work perpendicular to a force, meaning we have got gravity pulling this down, I balance it so there's no net force on this body. If I move it horizontally, I'm actually not doing any work because the forces are perpendicular to the direction I'm moving it. If I move the laser pointer up and down, I'm doing work. If I move it horizontally, I'm nominally not doing any work because it's not gaining any potential energy or it's losing potential energy. So no work is done here. The vector product, one application here is the torque. So you've got a radius r and a force F. So you've got some kind of origin around which you can rotate something. And the torque is a vector with direction perpendicular to r and f and magnitude given by the vector product. Who's cycling here? Most of you or many of you. If you pedal, where can you have the maximum effect? So if that's your front gear and you push, say you sit directly above it and you push down, where can you get the most torque? Where can you get the best acceleration for your cycle? If your pedal is down here, or if your pedal is there. I see some fingers pointing here. So if you push down here, you can get the maximum torque and the best acceleration there because you've got here the center of origin, you've got R here, you've got your force going down, they're perpendicular, and the torque T equals R cross F. And with that, the maximum is R, is of course when we have 90-degree angle there. If you can apply as much force down here, you're not going anywhere. Which direction does the torque show in this example? Yeah. It's definitely perpendicular to the blackboard because, as we've discussed before, it has to be perpendicular to both constituent angles. This one is pushing down, this one is pushing over. So we've got R going this way, the force going that way, so the finger is pointing into the blackboard. And the larger it is, the more torque you apply. Now, moving on to another key component which we'll need. So the differentiation. Differentiation is a way to find out the sensitivity of a function with respect to a variable. So if you differentiate with respect to that variable and you end up 0, the function you looked at was not sensitive at all, it didn't matter. If it's non-zero, the variable has some function. I'm not sure whether everyone has already done differentiation, so I'll quickly write down the basic basic definition. So if you have a function of a variable a, you differentiate it, or with respect to a is the limit of a little difference going to 0 between f of at point a plus h minus f a over h. So that's it. That's the definition, and we use that up and down. If you haven't seen this before, I suggest you pick up any calculus textbook and quickly read up on it. I hope it becomes apparent in terms of the meaning in this lecture, but the underlying mechanics we really need to know by heart. Now, we've written down some examples here. In physics, the two main parts which we're usually interested in differentiating is one with respect to time. How does something change over time? And the other one is with respect to a spatial coordinate. So y is here dy by dt, and y prime is dy by dx. So this is kind of the space with respect to a coordinate and with respect to time. And if you have a vector a here, down here, and that changes over time. So we've got a t, and a short time later, the point, whatever it was pointing at, is up there. So this is a t plus delta t. That's a small time difference, and that gives us the delta a. So small difference. If we write that out in the 3D components, a t equals ax from ti plus a y of t and j plus a z t k. And then if we do the time derivative of it, a dot equals dA by dt, and then we get the whole bunch of those ax t plus delta t minus ax in the I direction over this delta t, and so on for all the others as well. And then this one doesn't change. What changes is the coordinate ax. So basically we get that a dot equals the time derivative of the x component in direction of I, time component in the y direction differentiated by time, j plus the time differential of the z component, k, and then we have differentiated the vector a with respect to time. Integration goes in a similar way, but it's the other direction. We'll use that later in the lecture, and the usual rules apply. So if you have dt of a cross b, you end up with chain rule. So you get dA over dt cross b plus a dB over dt. There's only one thing where you have to be very careful about. If you have, say, r dot r, and you want to take the time derivative of this, this is not dr squared over dt, but it's rather 2r dot r. Sorry, I should write a little bit more legible. So you have to be a little bit careful here and there. Now, going through a couple of more the key components, velocity and acceleration. So we have the same as before, we've got R2, R1, 2 points. So we've got basically some kind of origin defined. A body is moving through space. At T1, it's up here. At T2, it's down there. So that's T equals T1, T equals T2, where T2 equals T1 plus some small time step. And then we get basically, if we just write that quickly out, delta R equals R2 minus R1. So just use a different color. This is delta R. And then basically we end up with R dot equals the velocity as before equals, and that's the limit of delta t going to 0, delta R over delta t. So as it says that the velocity at any point is tangent to the path at that point. If you reduce that to 1 dimension, it's pretty straightforward. Most of you have already done that. In 1 dimension, you can drop the vector notation because there is no other direction, and write v equals dx by dt equals x dot, and positive in positive direction, negative in negative direction. So that's probably not a surprise. So let's do a quick example there. A body has a velocity v equals v0 at time 0 of minus 15 meters per second at a position x equals x0 equals 20 meters, and has a time-dependent acceleration a as function of t equals 6 t minus 4, and the overall units are meters per second squared. And then they want to know or ask what is the value of x in which the body comes to rest. So the body is shooting in a negative direction there, and we want to figure out the acceleration is in positive direction at some point if t is large enough. So when does it actually stop and shoot to the other end? As with every physics problem, and I can't stress it enough, setting it up properly, doing the right graph can really make a difference between solving it and not solving it. So we have this in 1 dimension, this line at x0. We have a certain velocity, v0. The body has a mass, and setting it up well, we have to find out how this body of mass m moves along the x-axis, and we have a force that is pointing in 1 direction. Now, we are given that a as function of t equals 6t minus 4. And I'm abbreviating a little bit the units just so that the overall dimensions of this line is meters per square second. And we otherwise have at x0, at time 0, it's at 20 meters. And we have that v0 is pointing negative in minus 15 meters per second. Now, acceleration is the differentiation with respect of time of velocity. So I'm just going to write a equals v dot equals 6t minus 4 meter second squared minus squared. If I integrate that, so I get the time a of t dt, and I get 3t squared minus 4t plus a variable c, constant of integration, and the whole line has the units meters to second minus 1. We know that at t equals 0, we are given that the velocity v0 equals minus 15 meters per second. So we know immediately if we plug in here time 0, and we have to get minus 15 meters per second, c has to be minus 15 meters per second as variable. We are interested in when v equals, so I'll quickly write that again, v of t equals 3t squared minus 4t minus 15, and again the line has meters per second now as units, and we want to know when this is 0. We solve that. It's a simple quadratic. So I can rewrite it as v equals 3t minus 3, t plus 5 over 3, and that's meters per second. And that's, I want to know when it's 0. So we get t equals 3 seconds as answer. So we know after 3 seconds, the mass comes to a rest and then zooms off to the right. If you want to find out the function or the position as function of time, we integrate again. So because that's position and velocity are related like this, and we end up with t cubed minus 2t squared minus 15t. We get another variable of integration, which we need to fix. So the whole line has the units of meters. And we know that with that, b equals 20 meters. Because if we plug in at time 0, we know x0 is 20 meters. If we plug in time 0, 0, 0, 0, the only term that left is b, so b has to be 20 meters. And so at v equals 0, so that's at 3 seconds, and t equals 3 seconds, we end up that this is at minus 16 meters. So the body zooms over the 0, 60 meters into the negative, and then accelerates out again. Vector acceleration is done the same way as before. I'm not going to spend much time there. You can look at the slides before and just replace r with v, and then you get with the accelerations. I'd rather do the last examples for the last 10 minutes. Some of you may have already done it in school or in some, yeah. Sorry, which one? Oh, yeah, sorry. Yeah, it should be a vector. Thanks for pointing that out. Nothing has changed there. It remains a vector. Yeah. Okay. Thank you very much. Sometimes when you're standing that close to the blackboard, it's difficult to keep the overview. This example, some of you may have already done it. It's a projectile under constant acceleration. So the projectile is kicked out at a velocity v0 at an angle theta. And then the question is how does the trajectory look like? How far does it go? In this question, we only consider projectile under constant acceleration, so gravity. There are a few things which we neglect. Any suggestions what we're gonna neglect in the simple example? Yeah. Air resistance, and the other one? Change in gravity as we go up. There's a third one. Yeah. Exactly. The Earth is rotating, so while you shoot out, the Earth might have moved on a little bit. And we're just dealing that with that in 2 dimensions here. So we're given a couple of conditions at time naught. It's stationary at the ground. It's going to kick up with V naught. And we have to work out how things work there. So we know that A equals dV by dt equals V dot, and V equals dR by dt equals R dot. Sorry if I forgot the vector notation there. And we have R equals naught at t equals naught. And we have A is a constant, which is important since we're going to integrate. Now, we'll start with this term and integrate it. So on the left side, we integrate from 0 to t, A dt prime. I'm using a prime here to differentiate that t from that t, or make it look different. Sometimes, otherwise you're going to lose a little bit track of what coordinates or what you have. A is a constant. I can move it out. I end up with t prime from 0 up till t. So that was the left part up there. On the right part, I do the integral from 0 to t of dv over dt prime dt prime. We end up there with v naught to v dv prime equals, and then we have from 0 to v. And if we put that together on the left-hand side, we end up with at. So this is this side. Here on the right-hand side, we end up with v minus v naught. So the velocity at time t equals v naught plus at. That's probably not a surprise. So this is our first part. We have the velocity now. If we want to get to the space, we have to do another integral with respect to time. And we'll quickly do that. I've seen already our visitors arrive. On the left-hand side, if I integrate the velocity a second time from v dt, and on the right-hand side, I rewrite the velocity as I've written up there. Velocity is dr over dt, and with that, I end up from 0 to r prime dr, change of variables. That's the left side of this graph. So basically, this one I've done down here. And on the right-hand side, I integrate from 0 to t v naught dt plus, and then we have the at squared term, at term, t prime. And if I put that together, I get something that probably is not a surprise for you. R equals v naught t plus 1/2 a t squared, as you've done many times in one dimension in terms of velocity and integrating up and down. Now, if we plug in now what we know about it, we have r has x and y coordinates, as has the velocity. So the velocity actually is velocity in x and velocity in y direction. And That's from the starting point cos theta in x direction and v naught sine theta minus gt, because a equals minus g and y in the y direction, or the unit vector in y. So this is then taking this bit apart. And if I continue with r as x and y, I basically plug this term in. I end up with v naught cos theta t and v naught sine theta t minus 1/2 g t squared. So I've gone through the calculations by using the vector notation all the way through and splitting it up in the x and y component at the end. You can also do it the other way around. You can start with simply writing at the beginning this term out and then do the integrations, and you should arrive at the same. Now, if you want to solve it for x and y as function of x, as you usually do, then you have to eliminate t somewhere. You do this here. You eliminate t in this equation, and you get, you can rewrite the whole thing as, let me quickly, well, running out a little bit of time. Just very briefly. So if you eliminate for t, you end up with a function y equals x, t equals, you get t equals x over v naught cos theta. And you can work out the trajectory at the bottom when you plug it in here, and you can work out then when the trajectory hits the ground again, because that's when y equals 0, and it's of course at x equals 0, and then further down. So it hits the ground at x over 2 g v naught squared sine theta cos theta. And the maximum range you can get, the parameter you have is you vary theta, and dx by d theta gives you a 0 for its maximum, and with that theta max equals pi over 4. So that's 45 degrees. You shoot it out. You get the maximum if you neglect gravity, changes with height, rotation of the Earth, and so on. Before I end, I have a quick example. This is a classic physics example. Where do you need to shoot or aim when the monkey drops at the same time as you pull the trigger? And then it's an example of that you can basically decouple horizontal and vertical components. They're independent of each other, as I've written here. I hope none of you has ever to shoot a monkey. And there used to be an experiment in this class for exactly demonstrating that. It was stopped after something was chipped out of the wall, and I don't want to go through all the safety forms, but fortunately someone has done it for us. And to illustrate where you need to shoot to hit the monkey or a falling object in general. So the trigger and the magnet are coupled to each other. And they play it through with a couple of examples and different velocities, different angles, and so on. So the vertical component, the vertical acceleration that's acting on the monkey and on the ball are exactly the same. Both are accelerating at the same time vertically. The only difference with the ball is the ball has also a horizontal component that is unaffected over this distance and at this velocity by the air resistance. So as you can see, the lecture theater is empty. Otherwise, probably they would not allowed to do things like that. And they are sure that no monkey was hurt as part of those experiments. Okay, with that, I would like to close for today, and I'll see you Monday next week, and I'll hand over to Catherine.